So hello everyone. Today in this video we are going to study the p-type and n-type semiconductors. So what are semiconductors? Why we are studying p-type and n-type? And what are conductors? What are insulators? And they are categorized based on which everything that we have studied in the last videos in the series of study of electronics. So if you haven't watched, please go and watch for your better understanding. Each and every word that I'm going to use in this video is already been explained in detail in the last videos. So if you want to understand the videos or the lecture or this concept in detail, please go and watch the previous lectures. So yeah, we'll start with the first N-type semiconductors. So we'll first read the definition and then we'll explain this definition. So when a small amount of pentavalent impurity is added to a pure semiconductor, it is known as N-type semiconductor. Okay, it is known as N-type semiconductor. So the small amount, yeah, exact figure I will give you at the end of the slide. Pentavalent impurity. Okay, the word penta means 5, valent means valence electrons. So what is pentavalent is 5 valence electrons. So impurity means it's actually not impurity. Impurity means with respect to the pure semiconductor, if another things is being added, this is termed as the impurity with respect to a pure semiconductor. Understood? The impurity is not impurity, it is with respect to a pure semiconductor because it is foreign element. So basically pentavalent impurity means the element in a periodic table are having the 5 numbers of valence electrons. So these we are adding to a pure semiconductor to make the n-type semiconductor. Now why we are making n-type semiconductor, why we are making p-type semiconductor, you will get in detail when we'll study the p-n junction diode, PNP transistors, NPN transistors. For now, you should understand the internal working, internal construction, and the basis of the N-type semiconductor and P-type. So, pentavalent impurities, as I told you, for your better understanding, download one peak of periodic table in which there's one column having the 5 numbers of valence electron, in which you will get to know the antimony, arsenic, and phosphorus. Yes, rest of the materials are elements are also there, but the bonding characteristics when taken into consideration, these three elements are practically feasible. So these are used widely. Antimony, arsenic, phosphorus, this is the homework for you. Get its atomic number and the electronic configuration. Okay. So you will get to know the each is having the 5 number of valence electrons. So impurity introduces extra loosely bound electrons as a donor atoms. Okay. In order to just remember, I will just give you a trick. And here starts, you can say the N means electrons, P means holes, positive, and means electrons N. So yeah, when we are adding the impurity, it is creating the number of electrons. How? See this figure. What is this figure? You remember we studied the last time the silicon structure, crystalline structure of silicon. Yeah, so these are silicon atoms and these are the covalent bond. This structure is made. Now what I am doing, as you can see, the middle one is not silicon. The middle one is the impurity, and which impurity I have used here is Sb, antimony impurity. What happens? So whenever an external impurity tries to fit in this structure, what happens? See, Sb is having 5 valence electron. So out of 5, the 4 electrons are shared in the covalent bond. As you can see here, 1, 2, 3, 4. 4 covalent bonds and 4 electrons are shared here. So 1 electron is setting free. 1 electron is setting free. So what is that setting free electron is doing? Basically, that electron is setting free and take part into the conduction, electricity conduction. So these are the covalent bond, these are the silicon atom, this is the antimony impurity, and because of that we have got into this structure a newly added electron. What happens after that? We are naming this impurity as a donor impurity. Okay, in a N type the impurities are called donor impurities, in P type it is called acceptor impurities. So why they are calling donor impurities? What they are donating is the electrons. Okay, before the impurity there was no any electron, after the impurity there was one free electron. So yeah, it is donating a free electron to us. But is that means that the structure is become negative in nature? No, material remains electrically neutral despite added free electrons. And what is the reason? Tell me, what is the reason? Yeah, if you have seen the last videos, you will get to know even if the electron is setting free here, the number of electrons is always equal to the number of protons that resides in the nucleus of this atom. So The protons having positive charge, electrons having negative charge, they cancel each other. This material remains electrically neutral. Now, if the structure is remaining electrically neutral, we'll see what happens in the energy level. Yeah, energy level. Donor level in the energy band diagram, it's free electrons movement into conduction band at a room temperature. See, donor level, as you can see here, the dotted one. This is the energy band diagram that we have already studied, where you know that this band is valence band, this band is the conduction band, the middle band is the band gap. This simply means that if an electron in the valence band want to go into conduction band, it has to gain this much of energy. But because of this impurity added, now this donor energy level has come over here. Simply it means that even at the room temperature, lesser the energy is required by the valence electron to get into the conduction band. This distance has become decreased, the energy has become decreased. Increased electron carriers sufficiently enhance the conductivity. Okay, because of that, what will happen if the lesser amount of energy is required by the valence electron to get into the conduction band, it means the conduction is increased, the conductivity is enhanced. Okay, here is some maths is there. Intrinsic silicon means the pure silicon. What was the case in the intrinsic silicon? One free electron for every 10 to the power 12 atoms. So at the room temperature, one electron was setting free for every 10 to the power 12 atoms. Now, dosage level means because of this impurity, what will happen? 1 in 10 million, okay, 1 in 10 million 10 to the power 7. So if I want to calculate the carrier concentration, you just have to do this 10 to the power 12 divided by 10 to the power 7. That means 10 to the power 5. We have increased the carrier concentration by this much ratio. Okay, so if I am adding impurity by ratio 1 in 10 million atoms, the 10 million atoms of silicon and 1 atom of impurity, it is setting this electron free, and previously it was setting this electron free. Now because of this impurity, now I can make this much carrier concentration, electrons are setting free in this much ratio, which is significant in number. Okay, so n-type conductivity, current is mainly carried by free electrons which are negatively charged. Okay, we have seen the current is because of two things. One is because of electrons and second is because of holes. You always remember in n-type the electrons are there, and because of the current is because of the free electrons. Next, we'll see this p-type semiconductor. Because of the time constraint, I am using the fast words, but for your better understanding, if you're not getting, you can rewind and watch and then take the advantage of this digital lecture. You can also turn the speed low so that you can grasp it at your level. When a small amount of trivalent impurity is added to a pure semiconductor, it is called as p-type semiconductor. So we have seen the definition of n-type. Now we are seeing the definition of p-type. So instead of pentavalent, here I am adding the trivalent impurity, and rest all the structure is same. Now again, what is the meaning of tri is 3 and the valent is valence, means valence electrons. Means here I am adding the impurity, means I am adding the external element in the periodic table having the 3 number of valence electrons. And which are they? So the examples of boron, gallium, indium, and for you there's homework of calculating the atomic number of boron, gallium, indium, and calculate their electronic configuration and justify why they are called trivalent. Okay, so yeah, boron has 3 valence electrons. Now see the structure. Okay, the structure is a silicon's crystalline structure that we have already studied in the last lecture. Now here this impurity is added. For example, boron is added. Now what will happen? It is having 3 valence electron. The construction remains same. Boron tries to fit into this construction. So what will happen? 1, 2, 3. Now it has 3 valence electrons. So 3 electrons are shared with the 3 covalent bond. But in the 1 covalent bond, 1 electron has shared by silicon, but hole is but one electron is not there. So if the electron is not there, means hole is there. As you know, the definition of hole is absence of electrons, right? So yeah, boron, and there is a void, means there is a hole, you can say, means the place supposed to be taken by electron, but electron is not there, means what is there? Hole is there. So incomplete bond results in a hole wherein the electron is missing. The electron missing means what is there and hole is there. The current conduction in p-type semiconductor is predominantly by holes. What is hole? What is hole current? How it flows? Everything we have seen in the last lecture. Please see. So yeah, we'll discuss the energy level of this. So effect of acceptor impurities on the energy level. What we have seen in the donor, let's just compare quickly. The energy level was here, energy level was here because of free electrons. Now the energy level is here because of free holes, right? You're getting my point? See, in the valence band, there are the electrons and holes, but we know that when the electron move from here to here, electron is here and hole is created over here simultaneously. So for your sake of understanding, I have shown here holes, and this is the acceptor energy level. Means the impurity that we have added is a trivalent, and because of that the holes are created, and the extra holes have uplifted the valency band energy till here. Okay, can you say that the band gap is reduced? Yes, it is reduced. Means smaller amount of energy is needed even in a balanced band to go into the conduction band. In both the cases, band gap has reduced. Okay, here because of electrons, here because of holes. So I hope I have given you a clear understanding between the N-type, P-type semiconductor based on the impurity crystalline structure and the energy band diagram. So we'll see the next lecture based on the PN junction devices, and thank you for watching this video.